Hey, welcome guys. So yeah, basically this video, I want to start talking about the back measure theory, and yeah, so this is a introduction video, and there should be 6 or up to 10 videos, right? So there are many measurable theory textbook, and the simple one that I will follow is basically just a routine. And after I talk the routines approach, maybe 10 videos, then I will go to the I will talk go to the Zigama approach. So they are a little bit different, but the key ideas should be the same. So this video just follow from my mathematical analysis lecture. So should be little bit not 100% real analysis part. So well, just this the back theory measure theory should be viewed as the some transition from the routine to sigma. Okay, but so this is introduction, and yeah, but I will try to be rigorous as I can, and build all the theory step by step. Okay, so hope you guys subscribe to my channel. So this video, let me just talk about some basic idea. So let me just give a definition of these set functions. So quick definition set functions basically just some simple notation. So let me just write down two notes, right? So this is the union, and this a minus b is basically x belongs to a, but x do not belongs to b. Yeah, so I use minus, and there's a so this is an intersection. Okay, so yeah, this is just the just so this set function means that it is just common operations in the set theory. Okay, so definition. So let's say we have a family of a set. So basically, okay, so let's say we have a set A, which is maybe not I maybe not use A, maybe say X, which is non-empty. And then let's say we have a family R, which is a set of the powers, the subset, I should say subset of the power set of X. So 2 to X is called a ring. Okay, so this ring is not in the algebra that basically there is two right, but still the same, right? You have two operations. So if A belongs to ring, and B, so given any two A and B belongs to ring, we have. So one is that A union B belongs to ring. So remember, this ring is a subset of power sets, right? But basically, each element in the ring is a subset of X, right? So basically, you can talk about a union. So we must have A union B in R, and the second operation is A minus B in R. Okay, so yeah. Okay, so from these two definitions, you can easily say that A intersection B is in R because A intersection B is basically A minus B. Okay, and let me just add another condition. So a ring R is called a sigma ring. So this is the basic setting of the measure theory, right? Because if you want to say that you can use a volume to set A and a volume to set B, then you should be able to talk about the volume of their difference and their union, right? So this is a common. If let's say countable union of AN will be R for every AN in R. So basically, any countable union of R will give you another element in R. Okay, and the same reason, you can easily show that if you do all the intersection, then it becomes A1 minus n from 1 to infinity, A1 minus AN. So simple exercise. Right, so this is A1 is in R, and by definition, they're all different. They're all union are in R. So by the property of the ring, So this in R. Okay. Yeah, so I define a ring and a sigma ring. Okay. Okay, so now we can define a set function. So let's say that we okay, so let me just write down. So we say a set function phi. So basically phi will assign every set. So phi assign every A belongs to the ring to phi A, which is in the so-called extended real system. So phi is a extended real system. Okay, so simply speaking, it's just that phi of A will be some real number, but can be infinity. Okay, or negative infinity. Okay, so this is the first statement. So first statement just say that it's just definition. We say that set function phi is basically so basically we said set function means that given any set, we will assign each set a number which can be real. By definition is real, but it can be infinity. Okay, the second definition is that we say phi is additive. If so additive means that it can be added, right? So it means that if A B intersection is trivial, then we have phi of A union B will be phi of A plus phi of B. Okay, so you can think this phi as a volume. So basically you have two different sets. The volume, if they don't have any intersection, then their volume should be their addition. Okay. Okay, so also there's a adjective called phi is countably addictive. So countably addictive means that if AI intersection AJ is trivial, it's non-empty for every I and J. Basically, you can collect countably. You can take, then you will have a countable of these right from 1 to infinity, right, to be the summation of it. And the thing is, extended real system, right? So I mean, it can be arbitrary, it can blow up, whatever, right? So I didn't care about what it converge or not. I mean, in this situation, I didn't care. Okay, so now, so now we finish some definition. Okay, so now let's see some simple consequence of this step function. Okay, so let me just write down. So consequence. Okay, so there are I think 4 consequences. The first one is that phi 0 is 0. Okay, so 0 means empty set in what I call phi. And the reason is that by previous one that if A, B, so I think so this one is an important one. So if their intersection are trivial, that means the phi A plus union B is phi A plus phi B, right? So this is trivial because I mean A intersection 0 is 0. So phi A union 0 will be phi A plus phi 0. This guy is phi A. So we tell you that phi 0 is 0. Okay. Okay, and the second one is also important. Say that if B is a subset of A, then you will get phi of B less or equal to phi of A. This is okay. So if phi of A is greater or equal to 0, okay, for all A. So basically, if phi of A is greater or equal to for all A, then if B is a subset of A, then phi of B is less or equal to phi of A. The reason is that A is equals to A minus B, right? Union B. Okay, so phi of A, since there are intersection is trivial, equals to phi of A minus B plus phi of B. So now if every set is positive, greater or equal to 0, then phi of A will greater or equal to phi of B. Okay, but this tells you that the phi of I mean, in every case, phi of A minus B will be phi of A minus phi of B. Okay, so using this, we can prove the following, which is this third statement, also very commonly used. So given any two, A1 and A2, you will get phi A1 A2 plus phi A1 intersection A2 will be phi A1 plus phi A2. Okay, so this is a famous result. So you can see now this phi looks like exactly the volume, or basically counts how many elements if A1 and A2 are both finite. Okay, and the proof is basically simple. You just consider A1 minus A1 intersection A2, right? So if you take this and the union of this, you will get what? So what is the union of this? So this is A1 and A2, right? So the union of these two are basically the same as everything. Basically, it's exactly the same as union minus intersection. Okay, and by previous results, that this will be A1 union A2 minus phi A1 intersection A2, and for this one, you will get phi of A1 minus phi of A1 intersection A2 plus phi of A2. So remember these two are disjoint, minus phi A1 intersection A2. So one of these will cancel. So you get phi of A1 plus phi of A2 equals to phi of A1 union A2 plus phi of A1 intersection A2. Okay. Yeah. So let's prove the theorem. This theorem, I think you can view is a very simple one. So let's say if phi is countably additive. So this is our first assumption, our usual setting. So additive means that two non-empty one, if you're two intersection on an empty, their phi will be additive. And the countably means that the countably of them, this is the truth. Let's say on a ring R. And let's say AN belongs to R, and then let's say we have A1 is a subset of A2, and keep going. And let's say I keep going, and let's say finally become something, right? So finally become something which A in R, and let's say A is U. Let's say A is every union, right? So basically, you take a infinite family of infinite set, and then you take A to be all union of it. Then as n goes to infinity, and phi of AN will approach phi of A. Okay. So proof is very trivial. So proof is just consider, let's say, put B1 equals to A1 and Bn equals to AN minus 1, and easy to see that their Bi intersection Bj is 0, empty. So you can take the countably using the countably additive. So you get phi of your AN equal to summation of phi of Bi I from 1 to n, and you take n goes to infinity, right? So which give you phi of A equals to phi of B I from 1 to infinity. Okay, so let's prove. Okay, so now we got some proper idea of sigma rings. Okay, so then let me just okay, so yeah, maybe next time. Yeah, so maybe next time we talk about the definition of the Lebesgue theory. And basically, the idea is that we start from define a volume of the box, and once we have the volume of box, then we can try to use so-called elementary set, and we try to use the outer measure. Then we use a closed set and open set to bound some set. Then we can define use the convergence to define which guys the back measure. We'll see you guys next videos.